In early 2020, a black hole roughly the size of a small city crossed paths with a neutron star. There was no flash, no flare, and no afterglow. The star reached a vanishing point and was consumed whole. Our only evidence of this event was a ripple in the geometry of space itself, recorded inside a 4-kilometer-long vacuum tube. For 5 years, researchers analyzed that faint signal as a textbook merger, assuming the two objects followed a perfectly smooth circular path. Standard physics models often assume orbits are circular by the time they reach this final stage. The math suggests that as a pair spirals inward, they bleed off energy and round themselves off, erasing any previous wobbles or tilts. A circle is a geometric record of isolation. It suggests a pair that spent billions of years side by side in a quiet corner of a galaxy, entirely undisturbed by the gravitational pull of any neighbors. In 2026, a team from the University of Birmingham and the Max Planck Institute reanalyzed those same 32 seconds of data. Instead of assuming the orbit was round, they used newer waveform models that allowed for ellipses and tilts. Their analysis revealed a different shape. With 99.5% confidence, the data showed the orbit was not a circle at all, but an ellipse. This comparison shows the exact deviation the team discovered. Measured at 20 Hz, the eccentricity came out to 0.145, a specific stretch in the path that circular-only models were never designed to see. This tiny elongation suggests a more social history. For an orbit to stay eccentric right up to the moment of impact, the pair must have been pushed by an unseen companion or crowded by a neighborhood of nearby stars. Gravitational waves normally act as a cosmic sander. As a pair orbits, the waves carry off orbital imperfections faster than they shrink the distance between the two bodies, which usually results in a nearly perfect circle at the end. Because this specific orbit resisted that rounding effect, its signal sounded different. Instead of a smooth, rising chirp, it produced a modulated frequency, a wave that trembles as the objects spiral inward. Each time the bodies pass their closest point, the periastron, they emit an intense burst of gravitational radiation. As they swing out to the farthest point, the apastron, the emission drops. This alternating intensity creates the tremble used to map the collision. Detecting this specific modulation provides physical proof that the orbit was kept elongated by an external force until the final fraction of a second. Several environments are capable of preserving an oval orbit against the smoothing of gravitational waves. The first candidate is a hierarchical triple system. In this configuration, a distant third star constantly tugs on the inner pair. This mechanism, known as the von Zeipel-Kozai leadoff resonance, converts the tilt of the outer star's path into a permanent stretch in the inner pair's orbit. A second possibility is a nuclear star cluster. In these crowded centers of galaxies, stars are packed so tightly that constant near misses and gravitational encounters scramble orbits, preventing them from ever settling into a circle. Finding an elliptical merger means our census of these pairs is incomplete. We now have to consider formation models where these systems are born from crowded interactions, rather than living their entire lives in isolation. This discovery follows a path first walked 4 centuries ago by Johannes Kepler. By identifying that planets travel in ellipses rather than perfect circles, Kepler provided the geometric foundation that allowed for the development of modern gravity. Today, we are observing that same geometric shift in the most extreme environments we can measure, places where gravity is strong enough to compress a sun's mass into a sphere the size of a city. Just as Kepler's work corrected our view of the solar system, this shift from circles to ellipses forces a recalculation of how many of these extreme pairs form in the dense, chaotic hearts of galaxies. The merger of GW 200105 left behind a single black hole, 13 times the mass of our Sun, now drifting alone in intergalactic space. The third companion, or the cluster of neighbors that shaped its path, is likely long dead or scattered, forever beyond the reach of our telescopes. This marks a shift toward a more forensic style of astronomy. By measuring the residual curve of an orbit, we can find evidence of a system's long-vanished family history written into the shape of space-time itself. If you enjoy these deep looks into how we read the history of the universe, consider subscribing and liking the video. Which formation channel do you think is the most likely culprit for this oval orbit? Let me know in the comments. Until the next signal arrives, keep looking up. The geometry of the sky still has plenty of secrets left to tell.